Hello, everyone, and welcome to another exciting episode of York Observatory YouTube, or as we like to call it, TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I have been your setup person today, and my name is Dr. Elena Hyde, and I'm very, very glad to announce that we're broadcasting tonight live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. Just as a reminder, York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time, and tonight we have a really wonderful program lined up for you. Our hosts, Gagan, Palvisha, Noah, Sana, and special guest host, Professor Paul Delaney, will be going ahead today with a really unusual TeleTube, our first ever interview with Professor Marshall McCall. Take it away, Professor Delaney.
Just making sure that my unmuting button works. I was having a little bit of difficulty there. And thank you very much, Elena. Wonderful to be with you tonight. Welcome to the York University's Wednesday night presentation. As Elena indicated, our special guest tonight is Professor Marshall McCall. Marshall and I go back a long way. In fact, a very long way. Marshall joined York University back in 1988, get that right, get the right decade, and that was actually 2 years after myself. So he and I have been at York for well over 30 years. All sorts of wonderful things have happened in that period of time. The astronomy program has really come to life, and as you will find out very shortly, in large measure that arose because of his efforts. But more about that in a moment. Who is this guy called Marshall McCall? Well, just the brief intro. Picked up his bachelor's degree, Bachelor of Science, over on the west coast of Canada, the University of Victoria. Lovely little spot there on Vancouver Island. He then charged south into the United States and to the University of Texas, which is associated with McDonald Observatory, picked up his PhD. He then saw the light and headed south, all the way south to Australia. Checked out the southern sky, the Southern Cross, the large and small Magellanic Clouds, the Milky Way, which spans the overhead night sky beautifully, and he was in Canberra, the Mount Stromlo Observatory. As I indicated, he ended up back at York University in 1988 and has been there ever since. He's kept himself fairly busy in that period of time. Other than obviously teaching astronomy courses, he was the architect in large measure for the astronomy stream. So for those students who have graduated, including many of the students who are with us tonight who will be graduating shortly from the astronomy stream, well, it was Marshall who put that in place, and he can correct me in a moment if I am misspeaking, but it was in and around 1992. So we had astronomy courses at York prior to that, but they were, if you will, a part of the physics degree, not a standalone astronomy specialization. And he brought that into play back in the early 1990s and has taught almost uninterrupted our second year course in that period of time. So since that moment in time when the program came into existence to today, galaxy hunting, galaxies and cosmology, that has been the course that has been Marshall's domain almost exclusively. And we'll hear a little bit more about that later on, because it is arguably one of the most exciting of the astronomy courses because of the observational component. I'm biased, I admit it, but the observational component of that course really adds a great amount to that particular course. So that is the astronomy stream, in many ways a legacy. A couple of fun facts about Marshall, and I'm not going to roast him unduly, but interestingly enough, he and my wife both ended up at the same high school there in Victoria. So going back into the 80s. It is a small universe when all is said and done, because I would never have thought that that would have been a period of overlap for the two of them. But indeed, It was. I don't think they actually knew each other. High schools tend to be a little on the large side. Certainly, in the 30 odd years that Marshall has been here, the astronomy program has grown significantly, and now is a vibrant collection of astronomers. And of course, we are known for our public outreach activities as well. And there is this little telescope on campus, the 1 meter telescope, the largest telescope on any university campus in Canada. And Marshall's efforts, particularly as the chair of our department over the last, I think it's 11 years, and again, he can correct me if I'm wrong in that regard, certainly instrumental in making sure that we have a strong observational presence for our students, because that telescope we let our students loose on at every opportunity. So Marshall has had a terrific career, and I haven't even touched on his research activities. As I said, primarily a galaxies kind of guy, but there's lots of those sorts of questions that we're going to hear from our students who are going to interview him this evening. So on a personal note, thank you very much, Marshall. It's been a terrific 30 years with you, 30 plus years, seeing the group grow as we have, seeing all of our wonderful students graduate and go on to bigger and better things beyond the boundaries of York University. You can be dutifully proud, mate, in your contributions to that. So with that as an introduction, let me hand off to the student team, and I think Sana is on deck first.
We'll just give a little second. Marshall, feel free to have any rebuttal that you'd like from your introduction. And make sure to unmute yourself.
Yes. Thank you, Paul, for that interesting introduction. I really appreciate it. A couple of corrections. First off, we actually met in 1986 at McGraw-Hill Observatory, amazingly. Before either of us worked at York University, I was observing and you were working there.
That's right. I had completely forgotten that. Absolutely. My gosh, that's, Kitt Peak Observatory, or the Kitt Peak Mountain there in Arizona. That's right. The McGraw-Hill Observatory, where I heralded from before I came up to York. Quite correct, Marshall. Grand memory, mate.
And my term as chair goes back 15 years, but with 2 one-year interruptions for sabbaticals. The best part, though, is that I will no longer be chair in 7 days. And I'll finally be free to go back to doing research full time, on sabbatical, I might add.
Excellent indeed. 15 years seems like yesterday, right?
Yes, right.
Okay, all right. As I say, I will hand you over to our students.
Well, thank you, Professor Delaney and Dr. Hyde for the introduction, and thank you to Professor McCall for joining us tonight. The other hosts this evening will be Gagan, Palvisha, Noah, and myself, Sana. We all have some questions prepared for you, Professor McCall, about your research and your time at York University, starting off with Gagan. So take it away.
Hello, Professor McCall. I'm Gagan, and to begin with, we'd like to know a little more about your area of focus. So as an introduction to us and our viewers, could you tell us what is a galaxy and what is a galaxy cluster?
Happy to do so. Actually, I ask the first question every year on my final exam in my course, Galaxies of the Universe, is, what is a galaxy? And remarkably, most people get it wrong. And I guess that's a testimony to how bad a professor I am. After a whole course on galaxies, people can't answer the question. The reason is because it's hard. It's a hard question. When is a collection of stars a galaxy as against a star cluster, for example, right? That's fundamentally what we're dealing with. Galaxies come in various forms. There are galaxies that don't have gas, that there's galaxies that do have gas that is exclusive from the stars. So that's not a criterion to determine whether or not you have a galaxy. And galaxies have lots and lots of stars, but there are tiny galaxies with maybe 10,000 stars that are known. And then there are monster galaxies with 300 billion stars, like the Milky Way. But the smallest ones are in the realm of the population of a star cluster. So what's the difference between a galaxy and a star cluster? Well, for one thing, a star cluster is normally associated with a galaxy, some larger body. It's a part of it. It's attached to it dynamically through gravitation. But the fundamental difference that distinguishes a galaxy from a cluster of stars is the presence of a halo of dark matter. Clusters of stars do not have dark matter as far as we can tell, associated with them. And all galaxies do. And these halos can be very small for little galaxies or large for big ones, but they're always there. And so a galaxy would be regarded as an independent body of stars and maybe gas floating in space independently of other objects, and embedded in a halo of dark matter. So that's my answer as to what a galaxy is. Now, as far as a galaxy cluster is concerned, well, just like people like to join together and live in cities, galaxies like to gather in localized places in the universe, and making groups or clusters, a group being a small collection, a cluster being a larger collection. And in fact, there are groups, there are clusters of groups of galaxies that are actually called superclusters. And those are sort of the largest sort of structures in the hierarchy of galaxy organization in the universe. Make sense?
Yes, absolutely. Thank you. That was a great introduction. And why is researching galaxies and galaxy clusters important to astronomy?
Well, I think in astronomy, we always are interested in origins, right? And so, and origins mean, well, how we came to be. So we are humans. We live on a planet called Earth, but Earth is not just a planet. It's sort of it's orbiting a star called the Sun, and the star is just one of billions of stars, and it's in orbit around a center, which of a great body known as the Milky Way, and the Milky Way is a galaxy. So knowing about galaxies generally helps us to understand about our own neighborhood, namely the Milky Way galaxy in which we live. So from my perspective, my interest in galaxies stem from wanting to know more about how we came to be, particularly in our place in the Milky Way.
That's very interesting. The origins of space and astronomy have always been something that has been a real focus for astronomers. So that's awesome. And for my last question, what is your favorite galaxy and why?
Yeah, well, this may sound pretty obscure to you, but my favorite galaxy is known only by a number. NGC stands for New General Catalog. It appears in a catalog sort of established in the early 1900s called NGC 4395. Now, NGC 40, it has no other name. It has no name like the Pinwheel Galaxy. It's kind of an obscure galaxy in the constellation of Canis Venatici. It's kind of that's a northern constellation. And it's interesting because, well, it's rather innocuous in the sense that its brightness is rather low in an intrinsic sense. Its wattage is kind of like that of what we would call a dwarf galaxy, like the Large Magellanic Cloud, which is in orbit around the Milky Way. But it's nevertheless, it is like a spiral galaxy, but it only shows the barest hint of spiral structure. So what attracted my attention to this initially was a picture in a book known as the Hubble Atlas, and it shows that there are galaxies very far away that are actually shining right through it. So you look at this galaxy, and you can see very distant and apparently small galaxies just beaming right through the image of NGC 4395. So that's interesting because it tells you that NGC 4395 is transparent. You can actually look through it. And that's interesting nowadays because there was a time when people were suggesting that the so-called missing mass of galaxies, which we now attribute to dark matter, was a consequence of galaxies being filled with dust. And the dust was like a fog bank. So if you got enough dust in a galaxy, you can't see the whole way through. So when you try to measure the brightness of a galaxy and you don't know about the dust, you think the galaxy is there's a whole lot less stuff there than really is. It's mostly obscured by the dust. So this was actually a serious idea that was proposed to explain dark matter, missing matter, that we knew had to exist because of the way stars and gas were moving in galaxies. the gravity as a result of the gravity associated with the matter in them. But the fact that you can see right through NGC 4395 means that that can't be the explanation for dark matter, because the galaxy is transparent. It can't be. It's not a giant fog bank where we're actually able to see every bit of this particular object. The second reason I'm interested in this galaxy is because of an observation that I made when I was actually doing my PhD in Texas. So I was surveying balls of gas that glow by virtue of being exposed to ultraviolet light from very hot stars that were embedded within them. And I was picking out different targets to observe in different galaxies to study the chemical composition spectroscopically, which is a technique we use in astronomy to measure what chemical elements are composing the material that's glowing. And this particular galaxy right near the center had a blob that proved to have a spectrum that is a distribution of colors unlike any other of the balls of ionized gas that I was observing. And in my thesis and subsequent paper, I called this a Rosetta Stone because this particular object was unique. And I thought that it had the potential to yield insights into the centers of galaxies that perhaps at the time were not known. So subsequently, somebody went along and followed up on that Rosetta Stone and found that this object that I observed was a nucleus, a genuine nucleus for the galaxy, and that it was an active nucleus, which is an activity or is a signature of a black hole in the center that is glowing by virtue of material that is falling into it. Now, why is this interesting? Because NGC 4395 is the faintest galaxy intrinsically in terms of wattage known to have such an object in its center. Something called a liner, a low ionization emission region. And second, this black hole that's associated with the galaxy only has a mass is believed to be 100,000 times the mass of the sun, whereas all of the black holes in other galaxies known are much larger than that. And finally, well, one last point is that normally people believed that black holes are associated with galaxies with kind of a bulgy component in the middle. And NGC 4395 doesn't have one. So it's completely anomalous in terms of our understanding of the formation of bulges in galaxies and their association with black holes. So it's a very interesting galaxy.
We did ask you for your favorite galaxy, so I suppose it only makes sense. There'd be a lot of fun things to talk about. We are going to pull you away, though. Gagan?
Yeah, so thank you, Professor McCall. And up next, we have Palvisha with a few questions for you.
Hello, Professor McCall. I'm Palvisha, and today I'd like to talk a bit about your research. What research are you currently doing or are excited to do over sabbatical?
Well, I've spent quite a bit of my time studying the local organization of galaxies, and in particular, I have a special interest in something that is known as the local sheet of galaxies. It turns out that the Milky Way is a part of the local group of galaxies, which is primarily a binary system composed of Andromeda, which is like the Milky Way, and us in orbit around each other. In fact, we're falling towards each other, and we'll become uncomfortably close in about 3 billion years. That's another story. So the local group has all kinds of little dwarfs around it, little satellites, but also is a part of a larger structure, something like 20 million light years across. And that structure is known as the local sheet because every last object in that volume, 20 million light years across, is confined to a pancake that's 20 times wider than it is thick. So it's a truly flattened structure, but we're talking now on a very large scale, and we're talking about objects that are in this flattened structure, which are entire galaxies like the Milky Way. So this is a very interesting body, and because we're a part of it, it is yet a higher level of organization that you can regard as being relevant to our existence, right? How we came to be, because the Milky Way is a part of this structure known as the local sheet. Now, I did a lot of work mapping out the organization of galaxies in the sheet, and I found that the local group, of which the Milky Way is a part, is surrounded by sort of a roughly circular ring of giant galaxies. And they're at a distance of about 10 million light years from us. So that's 10 million. So there, now, whether or not that structure is significant from an evolutionary standpoint, we don't know. But what's really important to realize is that with a bunch of large bodies surrounding us, we basically have a collection of objects that are having a gravitational influence on all matter that may be associated with our neighborhood of the universe, in the sense that they are tugging on any matter in this vicinity in their direction, while the local group in the Milky Way are tugging on matter in local space towards our direction. And so I called this body, this collection of galaxies, the Council of Giants, because they kind of stand in judgment of the Milky Way and Andromeda by basically limiting their access to any reservoirs of material out of which they probably have formed, right? So the Council of Giants, I believe, has actually had a bearing on our evolution. So I've been, what I'm working on right now is looking for evidence that the Council of Giants has affected the flow of matter in our vicinity. And we believe, I worked with a student on this, an undergraduate actually, and we think we found evidence for a flow of material towards the Council on one side, the near side, and a flow towards it on the other side as well. In other words, that it is having a drawing power in gathering together little galaxies and making them move towards them. And of course, this is at the expense of us, because we lose access to the reservoir material that might otherwise make a body build to make us bigger places.
Thank you. That sounds incredibly interesting, and like just the impact that the Council of Giants and the local sheet has on the evolution of the Milky Way. So another question I'd like to ask you is what your favorite aspect of your research is.
I guess that's a good question. I guess it's exploring the unknown, right? Learning things that nobody else knew before. I enjoy working with students in particular, getting them engaged in research. I learn from them a lot. And actually, when you're a person that's been in my administrative position, sometimes that's the only way to make progress on research, is to have other people do it for you. So I really enjoy collaborating with students in particular on just exploring things in our universe, things at least I'm interested in. And I hope to continue that as I move forward, on my sabbatical.
Thank you. So I'm going to hand it off to Sana now for her questions.
Thank you. Hello, Professor McCall. I'm Sana, and I would want to ask you some questions about your time teaching at York University. So as mentioned before by Professor Delaney, one of the courses that you teach at York is the second year Galaxies course titled Phys 2070. And I took this course with you a couple years ago. It's got to be one of my favorite courses I've ever taken at York. And part of the reason for this is you did some really fun and interesting demonstrations in class about, one of them was about supernovas, and then you even demonstrated the evolution of a galaxy using, I think it was Kool-Aid. So could you tell us a bit about some of these demonstrations, a bit more about them, why you do them, how you came up with them?
Yeah, well, I just find, just listening to people talk all the time, particularly now on a computer, can get really challenging. It's hard to pay attention for long periods of time. So I like to do demonstrations to wake people up. And it's kind of a fun thing. And not only that, the demonstrations are things you can do yourself and show to your families and so on. And every so often I start thinking about, well, how can I explain a concept better through a demonstration? And you can imagine in astronomy, this is hard. Now, there's this famed supernova demonstration, which I can't claim credit for, This was invented by a supernova theoretician, actually, in California. But everybody who ever gives, people aware of it who are in the position of talking about the explosions of stars will use this to demonstrate, in blatant terms, how exactly a stellar explosion occurs. So that's really fun to do, but I'll tell you, it backfired once because one of the things I didn't appreciate is how rigid the floor or tabletop you have on which to bounce your balls. And I once was on this incredibly embarrassing position of giving a talk to potential students for York, right? People considering coming to York for their studies, where I did the supernova explosion demonstration, where you drop two balls at once, one just above the other onto a floor. And the top ball goes flying off and it'll go way up into the ceiling. In fact, one of the professors lost my top ball in the rafters of one of the big lecture halls once because of that. So, but anyway, it was a dud. They just sort of fell on the floor and didn't bounce up. It was just, and I tried it on a tabletop and it was even worse. But the reason is because the tabletop and the floor were not rigid, they bent. So energy from the balls got transmitted to the floor and none of it got transmitted back to the upper ball to make it fly off into the ceiling. Very, very embarrassing. So, but that's the price, that's the risk you take whenever you do a live demonstration. As for the demonstration of chemical evolution, I came up with that because chemical evolution of galaxies is very complicated. And you can write down all these mathematical formulae, rate equations, basically describe what happens. But nothing beats a real physical demonstration of what's going on. And I like to, well, I haven't really decided what's best, but you can either start off the topic by showing a demonstration, but I think it may be better to actually go through the rate equations and the general concepts of the whole idea of evolution, and then hammer it home with a demonstration at the end. I don't know, maybe you could tell me which way you prefer.
I loved those demonstrations. They were always so cool. And I think you're right when you say to kind of end on the demonstration, because it can help tie up any loose ends that you're having. It was a really fun class, a really fun project as well, which brings me to my next question, is that for our listeners, the final project in Phys 2070 is you use one of the observatory telescopes, currently a 1 meter telescope, to observe a galaxy. You take pictures of it and then you go and reduce those images, and you want to figure out if the galaxy has an active galactic nuclei, or an AGN for short. So Professor McCall, what is an AGN and why are they important for studying galaxies?
Well, actually brings me back to my favorite galaxy, right? An AGN is short for active galactic nucleus. And there are galaxies all over the universe. The most luminous examples being quasars, which are quasars are active galactic nuclei associated with a galaxy that you can't see because the light of the quasar, the nucleus, overwhelms the light of the galaxy. So they are regions in the centers of galaxies that were very prominent in the past, but for which the activities died down subsequently, where there is a supermassive black hole that happens to be accreting material from the gas and stars around, mostly gas in the early days. And that accreted material gets very hot and it starts moving very fast as it spirals into the black hole. And it basically creates a lot of light that we see as an active galactic nucleus. But the heart of it is a supermassive black hole. So we can learn a lot about the process of galaxy evolution on the one hand by looking at activity in galaxies as a function of distance, in other words, time into the past. We can learn about supermassive black holes and how they operate. We can learn about the development of structure in galaxies since the black holes formed. We can learn about how evolution of galaxies is affected by what's called feedback, where material that falls into a black hole is then blown out as a jet in two directions, thereby inhibiting subsequent star formation because the gas has been lost. Also, all lots of things can be learned from active galactic nuclei.
Yeah, I remember doing that project, and it was really fun to be able to get some some hands-on experience with galaxies. And when I did it, we had to use the 60-centimeter telescope, but now students get to use the 1 meter, which is always amazing. So I'm going to pass on. Sorry?
I'll just say one last thing about that. One of our mantras at York is to establish a name in the realm of practice. And in astronomy, we've got people engaging with telescopes from the very beginning, year 1, year 2, all the way through the program. And I think it really makes a big difference. People appreciate it, for one thing. For another thing, they learn a whole lot from actually having their hands on a telescope and the detectors that go with them, and then the data processing that goes after that, far more than they would learn by just being handed data and being asked to process it. I mean, you learn by having things fail, right? And when you're up in the dome and something stops working, you really learn a lot in a hurry, as compared with just, having somebody else make the observation. So that's what we try to do, is get people to become one with the universe by actually being up in the dome at night.
Absolutely. Nothing beats getting hands-on experience with telescopes, especially the kind that we have at York. They're amazing. So with that, I'm going to pass on the next set of questions to Noah.
So hi, Professor McCall. I'm Noah. As an aspiring astronomer near the beginning of my academic journey, I was hoping to ask you a few questions about amateur astronomy, outreach, and background that may help people in a similar position. So first of all, you mentioned that your interest in galaxies began because of your curiosity of our own origins. But I was wondering, what inspired you to pursue astronomy in general?
Well, this goes back a long way. I've always wanted to be an astronomer as far as I can remember. My earliest memory of anything related to that is when my mother took me by the hand outside at night to my backyard in Victoria to go and watch Sputnik. Now, I don't remember seeing Sputnik, but I do remember being really excited to be able to go out at night. So that's how my interest in astronomy, I guess, began. But as far as actual astronomy as against space, I remember starting to want to become an astronomer around grade 5.
That's amazing. And then now here you are. So just building off of that, do you have any tips or advice you would like to give to aspiring and amateur astronomers? Anything important you've learned throughout your journey? I know you mentioned just now that you learn from having things fail, and it's important to get hands-on experience, but what else? Do you have any other tips or advice that you'd like to share?
Yeah, well, there's two aspects of this. One is advice for amateur astronomers, and then the other is advice for people who want to go beyond that and at least get a bachelor's degree in astronomy, and maybe go beyond that to become a researcher in astronomy. So I was an amateur astronomer. I was observing, the satellites of Jupiter and measuring their periods, and Delta Cephei to measure its period, and all kinds of stuff like that. But I guess from an amateur standpoint, my greatest enjoyment was actually came from looking with my eyeball through the telescope. And as a professional, I enjoy that even more now, because all we ever do is we take pictures with electronic cameras, and it's a whole lot different to just see a picture on a computer screen as against to see something with your own eye. So I really enjoy looking at things with my eyes, and I encourage amateurs to continue to do so, even though they might like to play around with more sophisticated instrumentation. Insofar as going beyond amateur astronomy, I think the important thing to realize nowadays is that astronomy is a whole lot of physics and mathematics and computing, much more so than it was in the past. In fact, I would say most astronomers spend most of their time in research sitting in front of a computer screen. And nowadays, they don't even let you go to observe at the larger observatories. There's a system called Q observing, where you submit a proposal justifying your need for telescope time, and if it's accepted, it gets ranked, and people at the observatory, like in Hawaii or Chile, they will observe targets in order of rank until the number of clear nights runs out for the semester, which would be 6 months. So it's not, to me, as enjoyable as it used to be, because I don't get to go to observatories anymore, unless they're small ones. So people who come to York are very lucky because they actually get to observe with a telescope. Then you might ask the question, well, if I'm not going to be able to go to observatory, why should I bother learning how to observe with the telescope in the first place? And I would argue that the reason is because you can't appreciate data until you know about its imperfections. And you learn about imperfections by actually trying to acquire it yourself and seeing the obstacles that you face in the process. So, so if you want to go into a career in astronomy, you cannot compromise mathematics, you cannot compromise physics, and the more computational expertise you can gain, the better.
That's amazing. Thank you. That's really interesting and inspirational. But that's pretty much it for amateur astronomy and outreach. So thank you so much. Now I'm just going to pass it back to Gagan.
I'm actually going to just hijack us here for a moment. We are just about done with our regular questions, but we do have a few extra questions. And I think we're going to have enough time to do one or two of those. So I'm just going to sneak an extra question in the end here. Can you tell us a little bit about, you have been at York for a while, as was alluded to in your introduction. What are some of your do you have a top sort of telescope moment at York?
A top telescope moment? That's a good question. Yeah, I can't remember one. Mostly other people observe and I just tell them to observe. Well, I would say the big telescope moment is coming because right now we're actually putting together an instrument with, in fact, Professor Delaney involved that is going to allow us to do imaging with an electronic camera of wide fields for the purpose of detecting extremely faint extended sources. And by that, I mean nebulae, like the Orion Nebula, but more importantly, extremely faint, the extremities of such nebulae. You might ask, how in Toronto is this possible, given all the light pollution? Well, it's possible if you actually narrow the window of colors at which you look. So if you have a filter that you impose between you and the sky that emits only one color of light, like red, and that color happens to be a kind of light that is emitted by a nebula, but not emitted by the night sky very well, then you drastically improve the contrast between your nebula and the night sky, and thereby can detect things that you wouldn't be able to detect, say, with a filter that transmits all the colors, like your eye. So we're hopeful that this instrument called QUAIL, which stands for Quad Array of Isolating Lenses, is going to reveal things that heretofore we have not been able to detect from the York Observatory, and maybe things that have not even been detected by anybody, depending upon the filters that we actually use.
Excellent. Well, that actually, interestingly enough, I didn't think there would be a segue to my next question, but this does actually provide one. Because of the narrow range of light you're looking at, you sort of hone in on specific wavelengths. So I thought I'd try a little bit of a fun question. If you could choose to be any type of light wave, which would you choose and why?
Oh, I have an affinity for green. The reason is because since my earliest beginnings, I've been a big fan of the Great Nebula in Orion, and it was bright enough that you could actually see color. Most things that are extended nebulae in astronomy just look like gray because they're too faint to stimulate the parts of your eye that are responsive to colors. But the Orion Nebula is bright enough that you can actually see a greenish hue to it. It's a beautiful object. The reason it's green is because it actually happens to be glowing extremely brightly in a particular shade of green. And that shade of green originates from atoms of oxygen that have had 2 electrons removed from them. And there are collisions going on in the gas that excite these atoms of oxygen. And after they've been excited, they like to go back down to where they started. And when they do, they lose energy in the form of light, which is green. So That's the answer. My favorite color would be the green of the Orion Nebula.
Thank you very much. That's a wonderful, wonderful choice. We just have one extra question from Sana.
Yes, so I was wondering if you could tell us about some of your favorite, maybe fun facts about astronomy or your favorite story from your career or work as an astronomer.
Let's see here. You know, I talk about various exciting things that had happened all the time with my family, but now I can't remember. Well, one of the strangest things that happened, it didn't really happen to me. But I went, strange, you say? Okay. Well, this is partly exciting and partly strange. I went to observe at the University of Toronto Southern Observatory in Chile, Las Campanas, Chile. And I had the good fortune of being on Las Campanas at the very moment that the supernova of the Large Magellanic Cloud, 1987A, was at its brightest. So I was lucky enough to see that supernova.
We do have, I think, just enough time for one sort of final rounding off question. We've been talking a lot about science and York. How about your favorite sci-fi? Do you ever like to combine sort of sci-fi theories and science?
Oh yeah, I'm a big sci-fi fan since a long time ago. I started off primarily reading my favorite writer was Arthur C. Clarke, and my favorite book from him was Childhood's End. And then I evolved, and in recent times, there's this, my favorite book transformed to Ender's Game, by Orson Scott Card. And then it transformed to Hyperion by Dan Simmons, which is just a stupendous book. And I also like reading books by Ian Banks, who you may know introduced names for spaceships, which SpaceX has actually adopted for various of their vehicles. But my favorite book of his is The Player of Games. And the reason is because that's one of the few, if not the only, novel that I've read in the realm of science fiction which transports you to another galaxy. In other words, outside the Milky Way. It actually, there's a game that has to be played by this individual who is in the Milky Way, but it takes place in the Large Magellanic Cloud. So that's a really fantastic book too. So yeah, I am a big fan of science fiction, and I enjoy reading, and I'm actually happy to say that in my last departmental meeting, my faculty gave me this incredible number of best-selling science fiction books as a kind of a parting gift. And it was really gratifying because now that I'm not going to be chair, I'll have a lot more time to actually read.
Excellent. Well, yes, and hopefully there will be some more galaxies far, far away for you to read about there. All right. Well, I think we are just about done with our question section. So if our staff cannot find any more, I think we'll just go ahead and round off here and say again, a huge thanks to everybody for tuning in, and thanks to all of our hosts, thanks to Paul Delaney, and most of all, thank you, Professor Marshall McCall, for coming on to this live stream. We just have a quick outro and we'll sign off. I'll hand it over. Thank you.
Thank you again, Professor McCall. This concludes our interview. Thank you all for tuning in. Everyone, you have been listening to the Alan I. Carswell Observatory's TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Sana, Noah, Pelvisha, myself, Guggen, along with Professor Paul Delaney. You can always connect with us on Twitter and Instagram with the handle @York Observatory, and check out our website for show notes, content, updates, and contact information at observatory.info@yorku.ca. Thanks for tuning in, clear skies, and have a good night.